Hello and welcome to another Common Core Algebra 1 video by eMathInstruction. My name is Kirk Weiler and today we're going to be looking at Unit 8 Lesson 7.5 on linear quadratic systems. This is a topic that wasn't originally in Common Core Algebra 1, but it's going to be coming at least to New York State in the coming years. All right? It's also a great topic that you've got all the skills and the knowledge necessary to actually do it. So we're going to jump in to looking at systems that are composed of a linear equation and a quadratic equation. Let's jump right into it. All right, linear quadratic system. So first, let me just review. A system is any set of two or more equations. But really, for people in high school math, almost universally a system is just two equations with two unknowns, x and y, a and b, whatever. Sometimes you might have to do three equations with three unknowns, but not in Algebra 1. Two equations, two unknowns. Solving a system just means finding all the pairs of variables that make both equations true. All right. Now, a linear quadratic system just means that we've got one linear equation, i.e. it's got the graph of a line, and one quadratic equation, i.e. it's got the graph of a parabola. So, somewhere there's my linear. So a linear equation like y equals 2x plus 7. Somewhere there's my quadratic. Quadratic y equals x squared minus 2x plus 5. All right? We want to solve systems that are comprised of one of these things and one of those. We're going to do them both graphically and algebraically today. Make sure to have those graphing calculators ready as we get into exercise number 1. All right, let's do it. Consider the system of equations shown below. We've got y equals x squared minus 8x plus 15 and y equals x plus 1. Okay, we've got our quadratic because it's got an x squared, and we've got our linear because it's only got an x to the first. Now, we want to solve this system of equations graphically on the grid provided. And you've been solving systems of equations graphically now for a couple years, both in 8th grade math, and we've done it a little bit already in Common Core Algebra 1. Solving systems of equations graphically just means finding their points of intersection. Where do they cross each other? What points do they share in common? Now, in terms of the quadratic, you're going to graph that by simply putting it into your graphing calculator, creating a table of values, and plotting points. Now, we've done this quite a bit in this course already. I'm not going to snap and bring up the graphing calculator and put it in step by step by step. I'd like you to pause the video now and try to graph this parabola. All right. Well, one thing I am going to do is just sort of magically have a table of values come up. Maybe try to get that cursor somewhere else. Apparently not. All right. There's our table of values. Of course, we can plot these points 0, 15, 1, 8, 2, 3, 3, 0, etc. But eventually what would happen is we would just get our parabola, right? Nice, smooth curve. Don't forget to label its equation. Now, for the linear equation, y equals x plus 1, we could totally make a table of values just like we did before. Or we could use knowledge that we know about the y-intercept and the slope of the line in order to just plot points. Now, obviously, for this linear equation, the slope, the coefficient on the x term, the number multiplying x, is 1. All right, which if you want to think about rise and run can be written as 1 divided by 1. And its y-intercept is just 1. So we could plot those points, right? And we would get this line. We'd start it with a y-intercept of 1 and then go to the right one, up 1, right 1, up 1, etc. To solve the system graphically just means to find the 2 points here and here, right, where the curves intersect. And those are specifically the points 2, 3 and the point 7, 8. All right, there's the solution to our system. Easy. But you should also know how to solve this algebraically, and that's what we're going to look at next. All right, in the same problem, letter B asks us to solve the system algebraically by using the substitution property of equality. Show the work that leads to your final answer. All right. Now, the substitution property of equality basically just says we can substitute equals for equals. So what that means is I'm going to substitute x squared minus 8x plus 15 in for the y in this equation. And that's going to allow me to write this down. Now, a lot of teachers, including yours truly, use a special phrase for this. We say, set the equations equal. All right, and what you're really doing there is you're doing the algebraic equivalent of figuring out where the equations cross, right? Where is this y value equal to that y value? All right, now I have to solve this. But to solve equations that involve x squared is more complicated than involving equations that only have x to the first. We have to use techniques like the zero product law, completing the square, the quadratic formula, etc. All the problems today are going to simply involve the zero product law, which means we have to rearrange this equation to get it equal to 0, and then we have to write it as a product. So I think I'm going to take this x plus 1, I'm going to subtract both an x and a 1 from both sides to get this side equal to 0. And we can actually do this all at once. All right, you could, well, I don't want to do that. You can do it in stages. You could subtract one and then the other, but I think that we've done enough of this kind of work to do it all at once. Nothing's going to combine with the x squared, but a negative 8x minus x is negative 9x. Be careful there. 15 minus 1 is 14. Now we have an equation, a quadratic equation, equal to 0, so we can use the zero product law. In order to do that, we need to factor that quadratic. Okay. Pause the video for a moment now and think about how that quadratic factors into the product of two binomials. All right, I know the answer, Mr. Weiler, I know. Of course you do. It factors as x minus 2 times x minus 7. And you could do a check, right? Negative 2 times negative 7 is positive 14, and then negative 2x and negative 7x would combine to be negative 9x. The beautiful thing about the zero product law is we can now say x minus 2 is equal to 0 and x minus 7 is equal to 0. Of course, adding 2 to both sides here gives us an x coordinate of 2, and adding 7 to both sides here gives us an x coordinate of 7. Those are the two x coordinates where the line and the parabola cross each other. But if we want to solve the system, we have to not only have the x coordinates, we also need to have the y coordinates. Now we have two choices. We can take these x coordinates and we could plug them up into this equation to get the y's, or we could plug them into this equation and it shouldn't matter which. In fact, if it does matter which equation we plug them into, then these aren't the right values. So it's a good check. But for now, what I'm going to do is I'm going to do the simplest thing I can. I'm going to plug them up into here. And all this equation says is take the x value, add 1 to it, and you'll get the y value. So in other words, when x is equal to 2, y is equal to 3. And when x is equal to 7, y is equal to 8. Right? And that is exactly what we found graphically. 2, 3, 7, 8, 2, 3, 7, 8. That's it. All right? Solving equations, right? Solving a linear quadratic equation algebraically is actually fairly simple. All right? Graphically, it's not that bad either, but of course you have to have the right sized graph paper, you have to have the right graphing window. It takes quite a bit of work as opposed to the algebra. Anyway, let me step back, give you a moment to write down anything you need to, and then we'll go on and do some more examples. All right, let's move on. Here we go. Find the 2 points of intersection of the quadratic and linear function shown below algebraically. Now again, we could do this one graphically, but it would actually be fairly difficult, and you'll see why once we go through the calculations. But to find the 2 points of intersection algebraically, all we need to do is set the two functions equal to each other. So step 1, set them equal to each other. And maybe make that look a little bit more like an x. All right? Of course, that could probably look a little more like a 3. What I'd like you to do now is pause the video, try to solve this equation, substitute back into one of these two functions to come up with the y values as well. Pause the video now. Take upwards of about 5 minutes to do this problem. All right, well, we're back. I wasn't going to pause for 5 minutes. Hopefully you paused the video and you worked through it. Just like before, what we're going to do is we are going to get this entire equation equal to 0 by subtracting a 5x and subtracting a 3 from both sides. We're going to get x squared minus 8x minus 20 is equal to 0. Make sure you've thought about that a little bit. We have negative 3x, negative 5x is negative 8x, negative 17, negative 3 is negative 20. Be careful in those stages. Funky looking x there. We now need to do a little bit of factoring. And I believe what we're going to end up having is x minus 10 and x plus 2. But again, we should check. Think about it. 2 times negative 10 is negative 20. Positive 2x, negative 10x is negative 8x. All right. We're getting there. We got x plus 2 is equal to 0. Subtract a 2 from both sides. And we'll have x equals negative 2. X minus 10 is equal to 0. Add 10 to both sides. And we'll get x is equal to 10. Again, this is great, but these are only the x values. We also need the y values. We can put them into either one of the two functions, but quite frankly, this is going to be the easier one. That one just requires us to multiply by 5 and add 3. So, maybe over here, when I have x equals negative 2, my y will be 5 times negative 2 plus 3. So that'll be negative 10 plus 3, and that'll be negative 7. So one point of intersection is negative 2, negative 7. And when x is equal to 10, we'll have y equals 5 times 10 plus 3, y equals 50 plus 3, or 53 for the intersection point 10, 53. Now, I want you to think about it just for a moment if you did this one graphically. If you did this one graphically, it would probably be pretty easy to find the intersection point negative 2, negative 7. That fits on a nice standard sheet of graph paper. But an intersection point of 10, 53, that would be much more difficult to see if you were plotting it by hand. If you had your graphing calculator, you could use the intersect command. You could continue to make the window large enough to find this intersection point, but still, it would be more challenging than just setting the two equations equal, rearranging the quadratic equation so it was set equal to 0, factoring using the zero product law to find the zeros, and then back substituting to find the two intersection points. Easy enough. All right, let me step out of the way and you can look at the work, write down anything you need to, and then we'll move on. All right, let's try a little multiple choice question, a little practice, okay? Exercise number 3. Which of the following sets represents the x-coordinates? So we only need the x-coordinates now of the points of intersection of the line and the parabola shown below. Pause the video now and try to find out which x-coordinates, right, solve the system of equations shown. All right, well, this one's no different than the last one or the one before that, although the factoring may have thrown you off, the zero product law work. So let's take a look. I'm going to set the two equations equal to each other. X squared minus 12x plus 7 equals negative 8x plus 7, right? Just like before, set the two equations equal to each other. But now I want to rearrange this equation so it's equal to 0. I'll do that by adding an 8x to both sides and subtracting a 7. Wow, that is some messy writing. Let's try that again. Plus 8x minus 7. All right, so far so good. X squared, negative 12x, positive 8x is negative 4x. 7 minus 7 is 0, so I'm not going to even write that, but then I'm going to have that 0 on that side. So, one thing that's a little bit different about this one versus the other two problems is that at this stage we typically had a trinomial that we then had to guess and check. Now you got to watch out for this one. It feels a lot like the difference of perfect squares, x minus 2, x plus 2. And if you got choice 1, that's what happened to you. This is not the difference of perfect squares. X to the first, right there, that's not a perfect square. This is simply GCF factoring. I can pull an x out of both of these. So I get x times x minus 4 is equal to 0. In which case, I get x equals 0, and I get x minus 4 is equal to 0. That first equation is done, but I do have to do a little bit more work with the second equation. But I find their points of intersection are 0 and 4. I can verify that's true if I want to spend a little bit of extra time by taking 0, plugging it into both equations and finding that y would be equal to 7. Also, I could put x equals 4 into both of the equations and figure out what the y value for that is. And because they would be the same, these two have to be correct. In which case, of course, their correct choice in the blank is number 3, 0 and 4. Again, that's not an intersection point. Those are the x-coordinates of the intersection point. All right, take a look, then we'll move on to one last problem. Okay, let's do it. So the last problem that we're going to look at today is a special linear quadratic system. You know, so far it seemed pretty basic. You know, I set the equations equal, or I graph them both, I find the two intersection points, I move on with my life. Okay, but let's take a look at exercise number 4. Consider the linear quadratic system shown below, y equals 2x plus 4, sorry, y equals 2x minus 4, and y equals x squared minus 4x plus 5. Letter A asks us to solve the system algebraically and show how we arrived at our answers. So let's do it. I'm going to just scroll this up a little bit. Pause the video now and attempt to solve this linear quadratic system algebraically. Show how you arrived at your answer. Go for it. Pause the video and take a little bit of time. All right. Well, just like before, what we're going to do is by substitution, we're going to set those two equations equal. X squared minus 4x plus 5 is equal to 2x minus 4. Okay, set the equations equal. Now, let's use our zero product law, or at least get ready for our zero product law by subtracting a 2x and adding a 4 to both sides. All right, that gives us x squared minus 6x plus 9 is equal to 0. Okay. Now I need to factor that. Okay, this is a full-on trinomial, okay, but it factors a little bit weird. It factors into x minus 3 times x minus 3. All right, and you can verify it, right? Negative 3 times negative 3 is positive 9, and then negative 3x and negative 3x is negative 6x. Now, what's the result of having x minus 3 times x minus 3? Well, what it really means is that there's only a single 0. You know, don't become so on autopilot that you say x is equal to 3 and x is equal to 3. Nah, x is just equal to 3. That is the only intersection point, a single point. In all the other ones, we always had 2 intersection points, but here we have just 1. Now I still need the y value. That's going to be simple enough. Maybe I'll just use my 2x minus 4 to figure that out. So we'll get y equals 2 times 3 minus 4, which is 6 minus 4, which is 2. Hey, Red, it's been a little while. All right, so we simply have that solution to our system. That's it, right? Now that's, again, fascinating, because in the 3 exercises up to this point, each time we had 2 locations of intersection. This time it appears that we have only 1. So let's see how that looks when we do it graphically. All right, scrolling down a little bit, letter B says solve the system graphically by graphing both equations on the grid provided. The line and the parabola are known as tangent to one another because they intersect but do not cross each other. Let's take a look at that. All right, how about this? Why don't you attempt to graph both the line and the parabola on your own, and then we'll go through it and see why it only has one solution. All right, well, first I think I'll go linear. My 2x minus 4, right? What I see is that my slope is 2, so 2 over 1. My y-intercept is negative 4, and therefore I can plot my line, right? I can plot my y-intercept at negative 4, and then I can go over 1, up 2, to the right 1, up 2, to the right 1, up 2, etc. And then connect with that nice line. With my quadratic, I would want a table of values. Where's my table of values? There it is. I'll go horizontal this time instead of vertical. Always good to show your table of values. Again, this is an issue of just putting this into the graphing calculator, going to your table command, generating these things, and then being able to plot the points. -110, 0.5, 1.2, 2.1, 3.2, etc. Right? You don't need me to read them all off. You plot all of those things, and you have your parabola. Okay? Now, keep in mind, the only place that the parabola and the line intersect, the only point that they share in common is that one, right there. The point 3, 2. Okay? Which is exactly what we found algebraically up here. There was only one x value. Sure, it occurred twice, but still, x equals 3 is x equals 3, right? And that led to this picture. A line that just grazes the parabola and then goes on just as it normally would. That's called being tangent to the curve. And you're going to see that a lot more in Common Core geometry next year, where you look at tangents to circles primarily. You'll also look at tangents to parabolas again. You can look at tangents to all sorts of different curves, but it's when a line just touches a curve but doesn't cross it. And that leads us to the last part of this problem. Letter C asks, how many different possibilities are there for the number of solutions to a linear quadratic system? So far we've seen that we could have 2 solutions. Those were exercises 1, 2, and 3. And we also saw that you could have 1 solution. That was this exercise. Is that it? Are there any other possibilities? Think about it, and it's especially helpful to draw parabolas and lines and see how many times they can cross. Think about it for a bit. All right, well, let's take a look. We could certainly have 2 solutions, right? A parabola and a line that intersect at 2 locations. As we just saw, we could certainly have just 1 solution. A line that is tangent to a parabola. It hits it at just 1 point and then kind of goes merrily on its way. But that's not it. There's one last one that hopefully is going to show up somewhere. It's gone. Well, I'll just draw it then. It was there originally. But of course, we could have the scenario where we have a parabola and a line that don't intersect at all. This would be 0 solutions. And I did have a nice little graphic for that, but somewhere it's missing on here and I can't see it because it's invisible. But that's it. A line can intersect a parabola twice, once, or not at all. So there are 3 different possibilities. And I hope that you realized that when you were drawing out pictures. I now need to spend some time and try to find my missing picture somewhere. I don't know where it went. Anyway, let's wrap this up. Linear quadratic systems are very similar to linear systems, i.e. 2 lines. You know, the big difference, of course, is with 2 lines, you can either have the lines intersect once, or you can have the lines be parallel and not intersect at all. With parabolas and lines, you can have them intersect twice, only once, or not at all. Now, you're not going to have to deal with the not at all situation in this course, because that really requires some knowledge about how to know that they don't intersect algebraically. You can obviously tell graphically they don't intersect because they just don't hit each other. But algebraically, it's a little bit more tricky, and that'll take some Algebra 2 work before you kind of get to that point. Still, solving them algebraically is simple enough. You set the linear equation equal to the quadratic equation, get it equal to 0, use the 0 product law with factoring, solve for your x values, back substitute to get your y values, and you can then find where the line intersects the parabola. All right, I hope this helps give you a little bit of a jump start on linear quadratic systems. I'd like to thank you for joining me for another Common Core Algebra 1 video by eMathInstruction. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.